All right. The next talk is by Vishnoi from Iterative, who will talk about slime models and sparse recoveries.
Thanks, Alex. So what this talk is going to be about is an algorithm for this problem of sparse recovery and its connection with an algorithm that is found in nature, in particular, something that slime molds use to find food. So let me start with the problem of sparse recovery, which is the following. You're given a bunch of equations over variables. The number of equations is, think of it as significantly less than the number of variables. So here you have 3 equations in 4 variables. So such system of equations have typically infinitely many solutions if they have one. And one of the heuristics which people use to find a solution or pick a solution from this infinite space of solutions is to find one which is the sparsest. And this problem finds applications in a wide variety of areas in science and engineering. I guess many of you have at some point or the other encountered this. So a bit more formally, given a matrix A, which is an n cross m matrix, and a vector B, the goal is to find a vector in this space Ax equal to B with minimum L0 norm. This problem turns out to be NP hard, and hence one approach to tackle it is to look for relaxations. The first relaxation that comes to the mind, admitting the fact that the hardness comes from the 0 or the sparsity norm, is to relax it to the 2 norm. And here, the problem really becomes the following, that if you're given this subspace Ax equal to B, find the largest L2 ball centered around the origin which touches this subspace. Okay, so that's the problem. Finding the solution to this is easy. We saw it in Alexander's talk as well, that this is just solving a linear system of equations, so that's good. However, if your goal is to find a sparse point in this subspace, then it is unlikely, and the reason is the strong convexity of the L2 ball. So one way you might want to deal with it is to, instead of looking for the L2 ball, you look at the L1 ball. So now we try to find a solution, try to find a point on this subspace which touches the largest L1 ball. So do the same experiment. At the origin, start growing an L1 ball until it touches your subspace. And at least from this picture, which is in 2 dimensions, you get some idea that maybe this is a better thing to do if you're looking for solutions which are more sparse. And indeed, this intuition was made precise by a large body and work by many influential people, Donohoe, Candace, Romberg, and Terry Tao, who proved that the solution to this optimization problem, which is an L1 optimization problem over a subspace, does indeed find the sparsest solution under what is called the restricted isoperimetry property. This is some property on the matrix A, which guarantees that if you solve this L1 minimization problem, you find the sparsest solution in the subspace as well. So it's not really a relaxation, it captures the problem exactly. The nice thing about this is that this is computationally feasible, at least in principle. This corresponds to solving some kind of a linear program. However, in practice, people prefer to use a very simple iterative algorithm for it, which is called the iteratively reweighted least squares method. So despite the fact that the problem can be solved using a linear program, there is an iterative method which relies on this observation I mentioned in the previous slide, that L2 minimization is computationally very cheap compared to L1 minimization over a subspace. So let's try to do the following. Let's reduce the L1 minimization problem to a sequence of L2 minimization problems in the following very precise sense. So the algorithm maintains or constructs a sequence of points starting from a point y0 on the subspace to y1 and from yk to yk plus 1. How does it do it is the following simple equation. It solves the least square problem except that it picks the weights of each coordinate as the absolute value of the y coordinates it has from the previous iteration. And so what might be the intuition for this? Well, roughly, if for some I you have already, it's close to 0 or even 0, then the weight becomes really large. And so you would not put non-zero weight on this point unless you really have to do it. Okay, so in particular, if this is really 0, then the weight is infinity, and so you would never put any. So once a coordinate becomes small, it tends to remain small. But that's a guiding heuristic. I think the main thing to note about this algorithm is it's really simple. Okay, so it's so simple. It has really a 2-line MATLAB code, and here is a rendering of it, which you can see how it actually computes the solution. So at every point, it just grows this L2 ball or an ellipsoid until it hits the space, and that's the new point. So it's a simple, robust, and distributed heuristic. The question is, does it converge, or if and when it converges, and if so, what is the time complexity of this? So the problem is that, as defined, this method can actually get stuck. So you can construct examples of subspaces along with starting points, which get trapped in certain suboptimal points and can never escape from there. Another obstacle to analyzing the convergence of it is the fact that each vertex of so as I said, that this corresponds to some kind of an L1 minimization problem, and each vertex of that problem essentially acts like a local attractor in certain directions, or in some sense a saddle point, and which might mean that you might have to go along every vertex before you reach or find the optimal point. So in some related work by Ingrid Dobeschies and her co-authors, and more recently by Beck, they considered a modification of this IRLS rule, where they add some small noise parameter in the denominator and give some results about the convergence of this dynamics with good starting points. However, the problem that they solve is slightly different than finding the L1 minimization, L1 minimal point over the subspace. Okay, so what do we prove? We prove two things. The first, which I find quite interesting, is that this algorithm, which is quite popular, turns out to be essentially identical to an algorithm that we found in nature. And the second of a result is that we use this equivalence along with the analysis of this natural algorithm, or rigorous analysis of this natural algorithm, to be able to give an analysis for this IRLS method. So concretely, we show that if you want to get within 1 plus epsilon multiplicative of the optimal solution, the convergence is in time, which depends on 1 over epsilon cube. Yes?
What do we know about solving this problem with other algorithms? Like, what is
You can solve it using linear programming.
But what would be sort of the benefits in terms of running time?
So this is a deep and philosophical question. I prefer to take it offline. I think that the point is why people prefer to use IRLS versus when you have linear programming solvers. I think it's first of all, it's simple. I think there are also robustness properties of these algorithms which are probably observed in practice. And also they are you can have massively distributed algorithms for these. So this is my guess. I'm not a practitioner in IRLS, so I can't really comment. But I think the fact that essentially a similar algorithm is found in nature seems to suggest that perhaps time complexity is not the only measure that we should treat an algorithm with. This is one measure for sure, and probably crucial for many applications, but there may be other important aspects to an algorithm. So, okay.
Sorry, is CFA the condition number?
No, CFA is not the condition number. It is some number which depends on A. And I will comment on it in a second. So I think let's look at an application of, or what is a special case of this L1 minimization problem. In fact, it's this undirected min cost flow problem where you're given a graph. And imagine you're given a source and sink, and your goal is to ship as much flow as possible from the source to a sink while minimizing the sum of the absolute values of the flows. Okay? So this problem actually can capture things like bipartite matching and even capacitated min cost flow and so on. So it can capture many combinatorial problems. And so what does IRLS? Well, IRLS applies because it's exactly in the setting of finding the L1 minimizing vector in a subspace. So what does it correspond to? It really corresponds to the following algorithm. That what you do is you maintain resistances for edges, and these resistances are precisely described by this quantity. So if your current solution, if your current flow candidate was YE of K, then you compute the new vector Y is really just the electrical flow corresponding to the demand B when we replace each edge with a resistor of value 1 over YE of K. Okay, so these are algorithms which slowly play with the resistances of the edges and compute flows in graphs. And what our result gives us for this problem is an algorithm. This runs in time mn over epsilon cube. There's nothing hiding now here, except maybe some log factors in m. This m comes from the fact that every step of it, which is solving a Laplacian system or computing an electrical flow, can be done in O tilde m time. And this n is this quantity that I mentioned in the previous slide in this setting. So the fact that these matrices are totally unimodular implies that this number is n. In general, it depends upon the maximum subdeterminant of this matrix A. So I guess one thing to note is that if you look at the history of the recent breakthroughs in computing max flows in graphs, they all essentially use some variant of this idea. Okay, that you view the graph as an electrical network. There is some way to adjust the resistances iteratively based on the current flow and end up computing combinatorial flows in graphs. Okay. So this was just a short interlude. Let's go to the second character in the talk, which is this algorithm and how it makes an appearance in nature. So here I'll show you a quick video for those of you who have not seen it. So what you see here is this organism, which is called the slime mold. And in this experiment, what has happened is that initially the slime mold was placed over the entire maze, and then food was, this was a bit fast. Let me just play it again. And then food is placed at two sources in this maze, at the two endpoints of the maze. And the organism, by essentially doing something along these segments, changes itself, it reorganizes in the maze and finds the shortest path connecting the two food sources in this maze. Okay, so this is an experiment which was done around 2000 or I think late 90s and early 2000. It got a lot of attention from both media and even in TVs. There were TV shows about slime molds. Okay, how does it do it? So the remarkable engineering that nature has provided it is the following, which allows it to do. So you can think of each of these segments in the maze that the slime mold is corresponding to a tube in which some liquid is flowing through. And you can see this in the video as well, that something is flowing through these tubular structures which are connected inside the maze. And the fact is that depending upon the flux of the flow through each of these tubes, it has this ability to control the diameter. And a bit more precisely, if the flow is, or if the flux is large compared to the current diameter, then the diameter increases in the next time step. And if the flux is small compared to the current diameter, then the diameter decreases. And this gives rise to the following mathematical model, which was used to describe its dynamics. If sigma is, so sigma is a vector, which corresponds to, for every edge you have the diameter there. So d sigma by dt, which is how the tubes are changing in their diameter, is equal to the magnitude of the flux minus the current diameters. So this is a coordinate-wise equation of a coupled set of differential equations. They're coupled because the flow or the flux phi depends on all the diameters. Okay, so this is a differential equation. And you may ask how the flux is computed. Well, you can argue using simple fluid dynamics that if you fix the diameters to sigma i's, then the flux is nothing but a least square problem, which is the following. So you can arrive at this from completely physics considerations. That this is what happens. You may ask what is the subspace Ax equal to B. I guess in this case, A is the incidence matrix of the maze, where the two food sources are labeled S1 and S2, and you can arbitrarily pick one and say that is +1 and the other to be -1. So you can view the slime mold in a maze as a collection of interconnected tubes whose diameter changes with time. And it was proved by Bonifaci and others, building upon some prior work, that this dynamical system always converges to a shortest path in a maze. So, a cool fact, and I think a nice observation about nature. So our first result, which establishes that this IRLS and the slime mold are essentially the same algorithm, requires a little bit more. It's not entirely obvious what the correspondence is. Well, it's clear that there is some connection because both of them seem to be solving in every iteration, or at least every time step, some kind of least square problem. What is not clear is what is the correspondence between the diameters and these y variables, which correspond to flow. So it turns out that the way to view that, the first thing we need to do is to fix time, because in one case time is discrete, and in the other case time is continuous. So we introduce a parameter h, which you can think of as a discrete, something which is between 0 and 1. 0 means continuous time, and 1 means discrete time. And then we introduce two sets of variables. Instead of, so both of these dynamical systems have one set of variables. So we introduce two sets of variables, one corresponding to each of them, and consider the following algorithm, which we call the meta-algorithm. So you have the y variables and the w variables. So think of w variables as the width variables, or these sigma variables. And the update is the following. So with respect to the weights w, you find the least square solution in the subspace Ax equal to B, and then you do the following. You compute the new point y prime as a convex combination of the old point plus this flow vector that you have computed. So remember that this flow vector q could have both positive or negative entries, so we have to be careful how we update the weights. So the weights are updated by the absolute value of this vector q. So weights always remain positive, because you start off with some positive weights, so you're always positive. The vector y can be both positive or negative. And now it's kind of, once you see this algorithm, you can see that a projection of this meta algorithm onto the W variables gives you exactly the Fusarium or the slime mold dynamics, and the projection of this dynamical system onto the Y variables gives you the IRLS. So we have this dynamical system which consists of twice as many variables, and it projects in two different regimes to these two. So this is how they are connected with each other. And in fact, our analysis goes from here to there. So it starts off with some analysis for the Fusarium dynamics and ends up actually proving convergence or running time for the meta algorithm, which then implies the convergence of the IRLS method, or rather a damped version of the IRLS method. Okay, so a few words about the convergence. So remember, these are our update rules. In our algorithms, we always maintain that we are in the subspace. So for all k's, ayk is equal to b. In addition, you can check that the algorithm also maintains the following property, that if you start with a vector w0 and y0, so that w0 dominates in absolute value y0, then this will always be true. And our goal is the following, that if I start with a point y0, whose value in L1 norm is at most m times the value of the optimal solution, in how many iterations can we get within 1 plus epsilon of the optimal solution? So we want to understand the number of iterations required to do that. And the key thing here is to come up with potential functions. So that's really where the essence lies. So how to analyze or how to track progress of such a dynamical system. And this is where the inspiration from the analysis of slime mold dynamics comes in. There are three natural potential functions which I can talk more about, but I'll just tell you what these functions are. So the first function is the cost function. So this is the sum of widths of all the tubes that the slime mold is using at time k. Then there's a natural quantity called the energy. So this is exactly the flux or the total energy consumed by this physical system at time k. And finally, there is this entropy-like quantity. I think Lorenzo mentioned something here about generalized entropy. It's exactly the Bregman divergence with respect to that, for those of you know. For those of you who don't know, here is a formula for the entropy difference between the optimal point and the current weight vector. So these are the three potential functions which are sufficient to explain the convergence of this dynamical system. And I'm not going to give you an elaborate proof. The proof is not difficult. It's a few pages of calculations once you realize what is there to be proved, and once you have the right potential functions. So here is a cartoon version of what are the two cases that show up in the analysis. In the first case, we are in a position where at time k1, there is a large gap between cost and energy. And here we can prove that in the immediately following time step, the cost of the solution drops a lot. Okay. And the second case is when the energy and cost are close to each other. So the difficulty is that even though they are close to each other, they could be quite far from the optimal value or the optimal cost. And here, surprisingly, the dynamics of the slime mold are designed so that one can prove that if it is indeed the case that energy and cost are close to each other and they're both far away from the optimal cost, then in the next step, the system reorganizes itself in this information space, and you can get a reduction in this entropy potential function. Okay. So this these are the two cases. Let me tell you that the two things that you need to prove. The first one, in the first case, all we need to use is the fact that the vector Q is this optimal vector in the sense of least square. So the vector that minimizes the least squares with respect to the current weights. The second step is actually more interesting, and it also ties up with the notion of width that Lorenzo was talking about. So one can prove that if I pick h to be epsilon over this quantity here. Okay, so this is a mysterious looking quantity, but nevertheless, if I can prove that if I pick h to be approximately this, then I see a drop in entropy. And this has something to do with the log function and so on. I'm not going to explain. The question is, how big can this number be? How big can this quantity be? So this is a notation where we are, for a vector x, we are using capital X as the diagonal of this. And it turns out that you can come up with some bounds for this number depending upon the maximum subdeterminant of this matrix A. And that's where, if it's a flow-like problem, then the maximum subdeterminant is 1, and so you can get good bounds. Okay, so this is all I'm going to talk about this connection. Let me tell you another dynamical system which was inspired by looking at the slime mold dynamics. It's a bit different. However, it's geared towards proving the general linear program. The general linear program is the following, that your goal is to minimize summation xi. You could have costs here, it doesn't really matter, where x is non-negative. And Ito and others, and Zhu and Johansson, gave the following dynamical system for computing solutions to this linear program. So what is the difference between this dynamical system and the previous one? The difference is that there is no absolute value here. So this number can be both positive and negative, and it doesn't really so this negativity can be a big problem here. And here they ask this question about whether a solution exists for all times, and if it does, then what is the convergence and complexity, and more importantly, what could this dynamical system be optimizing? So in a related work, we answer some of these questions. The first one is about an optimization viewpoint. So what exactly is happening? So how to think of this dynamical system? The observation is that this corresponds to a flow on a Riemannian manifold. And the Riemannian manifold that shows up is the following, that it consists of all points which are strictly positive and satisfy Ax equal to b. And the metric at a point x is the diagonal inverse. So if you're at a point x1, x2, then the metric is 1 over x1 and 1 over x2 at that point. And this defines this following inner product on the tangent space. And now you can show that if you compute the gradient of the cost function with respect to this metric, then you get exactly this update. Okay. So one has to change the geometry of this problem to understand this as some kind of a gradient flow. That's what we did. You may ask, what is this x inverse? And where does it arise from? There is a very simple answer to it, and that is the entropy function. So if you start with an entropy function h of x, which is summation xi log xi, and you look at the scale divergence between them, between 2 points, and you compute the scale divergence of 2 points which are getting closer and closer to each other, you get exactly this Riemannian metric out of this. These are all this is a well-known fact. So nothing here is really not known to the experts. Just putting things together is what we realized. And what this gives us, this optimization viewpoint gives us, is a reparameterization of this dynamical system as an interior point method with an entropy-like barrier. So imagine that you start off with some point in the domain, omega, and consider the following optimization problem where there is a parameter mu, which is something which is bigger than 0. So this was your cost function, and this is kind of like a regularizer. And as mu is going to infinity, the effect of the regularization is going to get lesser and lesser. Okay? And so a simple fact here is that as if I let mu to infinity, then the solution to this program tends to the optimal solution. And what we can prove is that this parametric solution, x mu, as a function of mu, satisfies the same differential equation that I showed you in the previous slide if I do a change of variables between mu and t. So in some sense, so in the previous slide I showed you how this the Feiserium dynamics, the directed Feiserium dynamics corresponded to a walk on a Riemannian manifold. Here you can see it as a parametric solution to a convex optimization problem. And this also gives a very easy proof of existence of the solution at all times. And interestingly, one can from this derive a rate of convergence for the directed min cost flow problem, which depends something like log 1 over epsilon. So this method, this method, it's not clear where it lies, whether it is closer to Karmaker's projective scaling or to the affine scaling. It seems like it's somewhere in between, because for affine scaling you don't expect such a convergence, but it's clearly not projective scaling as well. So there are some subtle differences, and it's, I think, an interesting problem to understand when this algorithm can be made to be fast when you discretize it. Okay, so I'll conclude. So in this talk, we saw some dynamics which were inspired by looking at slime molds and some connections to some algorithms which are at the center of many of the recent developments and also some of the old work in math programming literature, such as the IRLS, interior point methods, and network flow algorithms arising from electrical flows. All of these algorithms turn out to be very simple, experimentally robust, have very nice distributed implementations, and also prove a part of our work is to prove that they're correct and establish some preliminary complexity bounds. The main question that remains for the experts here is to try to see how fast you can make these methods. So just like in the case of electrical flows, by changing or coming up with more clever and clever ways to use electrical flows or how to update resistances, I'm hoping that some of these methods can also inspire such results for directed flows, and also prove some improved bounds on the method of IRLS itself. With this, I'd like to thank you for your time.
Questions?
Is there any consequence of anything like this to the actual natural algorithm so that the slime model can, I don't know, converge faster?
So sorry, can you repeat your question?
I mean, can we do anything to the actual natural algorithm on the slime model so that we can make them converge faster?
Not sure. Perhaps you'll have to go and do the gene editing.
We have very limited things to do, right? Maybe we can put some food, I don't know, in between to divide and conquer?
Or you could edit their genes to implement your algorithms. That's where you'll realize why simplicity of algorithms is such a big constraint in nature. Because in nature, these algorithms have to be passed from one generation to another. So, algorithms which are 70-page long are unlikely to be transmitted from one generation to another. So I think the other way is probably more interesting, to analyze these algorithms when they work fast. Yeah.
I guess that was exactly the question. Can you turn it around, and can we replace maybe big clusters of computers with big clusters of slime?
That so there are, this is again an offline topic of discussion. There are talk shows in Germany which talk about things like this, and whether this whole universe is inside a big slime mold. And I'm not joking. But my answer is I don't think so, because the time scale of this video that I showed you is not in real time. It's over several hours. Yeah.
I didn't quite get the connection to the interior point method, because it seems like, at least in the continuous time dynamics which you wrote, that you are doing some averaging between the previous points, and the most recent point is just with exponential weights. You can turn this into averaging. It's just with weighted averaging with exponential weights.
I don't see that, but I believe you. Yeah.
But in interior point methods, at least from what I remember, typically you're not doing any averaging.
But I mean, the sense in which it is, I would think of it as an interior point method is that there is a Riemannian metric which is guiding the trajectories. So there it's the Hessian inverse of the function, right? So here it's the Hessian inverse of some other function, which is the entropy functional. So in that sense, there is a connection. There is also a disconnect that this algorithm you can prove works no matter where you start from. You don't even have to start from a feasible point. And this is something I didn't emphasize. In interior point methods, it's usually difficult to ensure this. I don't know of an interior point method which no matter where you start from, it converges to the optimal point. This one does. We can prove that. So you don't have to start in the subspace. If you start from outside the subspace, you will still converge to an optimal point corresponding to the subspace, but only from outside. You will never enter the subspace. So that's something very curious about this method as well.
But isn't this thing that's before minus x generating a feasible point?
No. So this would be feasible if your initial point was feasible. If you start off with something infeasible, the dynamic still makes sense and it converges. Yes.
So just to make sure I understand, so the connection is, so if you start with a point on that central path, then...
Sorry, if you start?
With a point on that central path you define parameterized by that mu?
Yeah.
Then the continuous dynamics follow that path exactly.
Right. That's right. But that interpretation holds only for a start from inside the body. If you start from outside the body, these dynamics still make sense and actually provably converge.
On the body, start on that path.
Yeah. Yeah. If you start on that path, yeah.
Any more questions? If not, let's thank Nisheeth again.